All right. Hello, my name's Adam. I'm one of Zara's students, and I am going to be talking about some introductory topics to her talk later this semester. And it's going to be on character varieties in particular. If you have any further questions after I go through everything, please feel free to email me here. And yeah, let's get started. So to start off, this is the main property we're going to be talking about during this talk. Is proper discontinuity. So given a group G that acts on some topological space X, we say that that action is properly discontinuous if for all compact subsets of the topological space, the number of elements of G such that the image of the compact set still intersects its original space, that number of elements has to be less than infinity. And this is a nice property because when an action is properly discontinuous, then the quotient map from X to X mod the action is a covering map. Now, an illustrative example of this phenomenon is the action of Z squared on R2, where it's literally if you take a pair of integers and a pair of real numbers, the action is you add the integer to each coordinate. And let me draw that out for a sec. All right, so let's say we have R2, which looks something like this. And here are some dotted lines for the integer coordinates. Gonna be a very rough drawing. All right. And let me draw in an embedding of Z2 to start illustrating what happens. These points right here are the integer points. And the action of Z2 on the surface is essentially a translation from, like, say, the origin gets sent to whatever coordinate of Z2 you are at. So 2, 1 sends 0 to 2, 1. And that means that if you have any compact subset of R2, let's say a compact ball, a closed ball, there are only finitely many integer translations you can do that still allow that original ball to intersect itself again. Here, let me see if I can draw something quick. So like that's a ball. Any integer translation of this one actually will move it entirely off of itself. And even if it was slightly larger, like here, there are only finitely many Z2 integer combinations that you can shift this ball by to have it still intersect itself around some other coordinate. And so what this means is that when you try to quotient by the action right here, let me try to change the colors. Well, then every coordinate in the space is identified with something in this unit square right here that I'm highlighting. And so then, let's say like mod by Z2. So then we can just focus on this single square. And because the top and bottom sides are an integer apart, they're identified, and same with left and right. Hopefully you can see that now this space right here is the torus. If you try to glue things together, it ends up looking exactly like a donut. And there you have it. That means that R2 is a covering space of the torus, and it's simply connected, so it's the universal cover. All very nice properties. If you're more curious about this kind of covering map stuff, you can look up Algebraic Topology by Alan Hatcher. Now let me just erase all of this, and let's continue on. We're going to be talking about a certain group and a topological space to start off things. So our group is going to be the mapping class group of an orientable surface, usually. And this is going to be the group of self-homomorphisms of S that fix the boundary pointwise and also preserve orientation if the surface has an orientation. And then we quotient all these homomorphisms by isotopy. Again, an algebraic topology is a good book to look into. to learn more about that. And the classic example is the mapping class group of the torus is SL2Z. And I'm just going to use that as a way to know how big I can draw. If we take back out our drawing of the torus as being covered by R2, then we can look at some integer arrows that can represent our linear mapping of SL2Z. How SL2Z is going to act here is, let's say we take the matrix 1, 1, 0, 1. What this is going to mean is that, well, this is our vector 1, 0, this is our vector 0, 1. Let's just see where they get sent to by the regular old linear map here. Then 1, 0 gets sent to 1, 0. And 0, 1 gets sent to 1, 1. So the whole thing is shifted somewhat. If I could fill in, this is the original unit square that represents the torus. And now that unit square gets sheared over to this parallelogram right here. But because this agrees with the action of Z mod 2, this this action right here descends to an action on the torus. And there you go. Each matrix of determinant 1 has this action and can descend back to the torus, an action on the torus. And for more general cases, we can say that the mapping class group is generated by finitely many Dane twists. And now a Dane twist is done by taking some certain like portion of the surface, and specifically we take some simple closed curve on the surface, which is a loop that doesn't intersect itself. I want a better drawing than that. Here. All right. And there's just more surface to the left and the right, but we're isolating a cylinder around some simple closed curve here. And so to do a Dane twist, you first, a good way to visualize it is to cut along the surface. Just have it. Not along the surface. You cut along the simple closed curve to put the surface to. And then you glue it back together with a twist, quite literally. So let's say that, and I'll draw this a bit better. A good way to look at this is to think about a second curve, second line that just crosses the surface right here. And so then when you cut, it gets, it gets cut. But then when you glue it back together, we literally twist this thing by 2 pi radians. And so the curve ends up actually looking like this after the twisting is done. And that is a homeomorphism from S to S that is not isotopic to the identity when the curve, no, in all cases, when the curve is non-trivial. So there you have it. On the torus, the equivalent way of talking about the mapping class group is that this 1101 matrix is equivalent to Dane twisting around, let's say, this curve right here. And then the other Dane twist needed to generate the mapping class group is this one. The two matrices being 1, 1, 0, 1 and 1, 0, 1, 1. And these generate SL2Z. If you would like to learn more about mapping class groups, you can look into, let me write this down, a primer on mapping class groups by Farb and Margaret. So yeah, that's going to be our group. And on to our space that it's acting on. At least the first one for now. We're going to build up to the character variety topic eventually. So the Teichmuller space is based on hyperbolic structures on the surface. Now, a hyperbolic structure on some surface X, S, is a pair where X is a surface with a hyperbolic metric that is finite area and complete, and phi is some homeomorphism from S to X. This is not just directly a hyperbolic surface, it instead has this map here. And one way to think about the reason this map happens is it's a way to define a coordinate system on S. Maybe there are two equivalent hyperbolic structures, but at different points. They have different coordinates. And the Teichmuller space is the space of these hyperbolic structures. And the equivalence relation on it is such that two hyperbolic structures are equivalent when the transition map between them is homotopic to an isotopy. So essentially, these two structures, these two hyperbolic surfaces and their marking maps are only off by an isotopy, and then they're considered to be the same in Teichmuller space. Now, a way to give this what's essentially a set, a topology, is to identify it with this exact space of uh, representations of maps. So here, first, this right here is the set of discrete and faithful homomorphisms from the fundamental group of your surface into the group PSL2R, where PSL2R is SL to R mod the identity matrix and negative the identity matrix, which is the center of the group. And the reason that this is the case, well, let me talk actually first about why we're modding by PGL2R. Let's clear that. Give me a second. All right. And the way PGL2R acts on this set of homomorphisms. Oh, by the way, a faithful homomorphism is injective, and a discrete homomorphism means the image of pi1 of S, and here is just a discrete set. Each point is isolated from any other point in the image. But anyways, the action of PGL2R on here is by post-conjugation. If you have some matrix, PGL2R, where PGL2R is just GL2R mod the center of it. So GL2R mod all diagonal matrices. And so let's take some matrix that represents a point in here. And then the action of A on some representation rho is you just conjugate the image of rho by A. The reason that this is identified with the Teichmuller space is a couple of steps, and the proof is a bit more complicated than I'm going to show here, because this is sort of our first example. But let's say you have your space S, you have your map onto X via phi. One very useful thing to know is that any surface with a hyperbolic metric has universal cover the hyperbolic half plane, which is quite literally a half plane. You can embed it in R2 or C if you like. And this has a very natural hyperbolic structure on it, and it covers all hyperbolic metrics on surfaces or subsets of the hyperbolic half plane. And this is nice for a certain reason. So let's try to define our map given some hyperbolic structure here, x and phi, we can first start with pi1 of s. And first we map it over to pi1 of x, which is pretty natural. It's just the map induced by phi itself. This is actually a homomorphism or a isomorphism of groups. But the fundamental group of a surface is equivalent to the deck transformations on this covering map right here. And deck transformations for metrics are actually isometries. So this is a subgroup of the isometries on H2. And fun fact, that isometry group is isomorphic to PSL2R. So we've done it. This right here is what we will say rho is. There you go. And funny enough, this is in fact an injective map because this is a homeomorphism and we're just embedding it in the isometries. And it's also discrete for with more complicated explanations needed for that fact to be the case. But yeah, this is very nice because this set right here has a topology on it. It's a compact open topology is the name. It's for any space of maps, you can define that. And then you just use the quotient topology when you quotient. So to continue onward, now we can define our action of our group on our space. So the mapping class group acts on the Teichmuller space by this right here. So given a homeomorphism that is a mapping class group element from S to S, and some hyperbolic structure, some representative point in Teichmuller space, the associated action just takes these two and precomposes with theta. So all this does is essentially change the coordinate system. It changes the marking. So the actual hyperbolic surface itself is the same, but with just different coordinates. And the inverse here is just to make this be a left action, to make it be well defined. Fun fact, this action is properly discontinuous, the original property we described. And this is known as Fricke's theorem, made by Fricke. And it takes quite a bit of effort to make. But it has been found to be generalizable into character varieties, as I'll talk about further. And so just an equivalent way to define the action is because instead of this being a Teichmuller space point, we could have a discrete and faithful representation instead. And the way some homomorphism acts on that representation is, again, by precomposition. It works the same way. But this is a way more generalizable type of action. And just to talk about what this means, how does theta act on the fundamental group of S? Well, each oriented loop on the surface is in bijection with some conjugacy class of pi1 of S. And a mapping class element, homomorphism, does send each loop to some other loop. So it sends each conjugacy class of pi1 of S to a different conjugacy class. And so it's not quite well defined, except for we mod rho by conjugation in its image, in its codomain. And that happens to make it well defined. It means that all we need is an action on conjugacy classes. Now to start talking about generalizing this action, what other spaces can we talk about with a properly discontinuous action? And one thing to note is a slightly more symmetric definition. There are two copies of Teichmuller space in the set of all homomorphisms from fundamental group of S to PSL2R mod PSL2R. So this is now different from not PGL2R. If we instead only mod by PSL2R, well, those spaces are off essentially by an index 2 action. And so then there's actually two copies of Teichmuller space hidden in this. And those copies are connected components of this space, so they're open. Now, why is this interesting? Well, we can talk about this more general space with this idea with now PSL2R being here, PSL2R being there. If we have some finitely generated group gamma and some connected Lie group G, which is a space that is both a group and also a it is also a smooth manifold such that the multiplication map and the inverse map are smooth. Given those two things, we have an associated character variety, which is all homomorphisms from gamma to G, mod G, where this modding of G is exactly the same as we've done before. So if we have some representation rho, and the dot just represents an element in gamma, if A is some element of our Lie group G, then A dot rho is just A of the image of rho times A inverse. So exactly the same. And now if gamma is pi1 of S for some surface S, then the mapping class group acts on this character variety via precomposition. Again, that's where given some rho, you first apply theta inverse to it for some self-homeomorphism theta. When G is a semi-simple Lie group, and I'm not going to define that here, but that's a certain nice type of Lie group, there's often to be found a domain of discontinuity for this action, which means some subset of the character variety that is preserved by the action of the mapping class group, and the action restricted to the domain of discontinuity has to be properly discontinuous. And we often like to find open domains of discontinuity for the sake of being able to quotient nicely. Now, the example of this phenomenon is Teichmuller space in the character variety of pi1 of S and PSL2R. That is this right here. This is the character variety, exactly the same thing. And Teichmuller space is in, well, there's two copies of it, and both of them are open domains of discontinuity of the mapping class group action, as we've already talked about. And that's sort of how we have generalized our topic now. Now we're going to look about, okay, what subsets of these character varieties have a nice action on them from the mapping class group, a properly discontinuous action. Oh, and I should mention really fast that we often quotient by more. Let me just write that down. Because this space is not always Hausdorff, it's not always even T1, depending on how it works. So sometimes you quotient just by a bit more to make this space have nicer topology on it. But it depends on where you look. Gotta clear my notes. All right. Now we'll start talking about some structure on this character variety, some nice tools that we can use to analyze them. So in particular, if S is the one-hold torus and G is SL2C instead of PSL2R like we usually do, we have been doing, then their associated character variety can be identified with C3. This is a bit of a special case, but it's a nice case. Each representation in the character variety gets sent to the coordinates related to the trace of rho of X, trace of rho of Y, trace of rho of Z. And let me draw out what those are. And I'm just using the next paragraph to help me not draw too big. But let's take a little one holds torus. So that's the same as a torus, but there's just a open disk taken out of it, leaving this closed manifold behind. They're not closed. this compact manifold behind. And here, X can be this loop, Y can be this loop, and these two generate the whole fundamental group of the surface, actually. And then Z is going to be their composition. So you loop around, and then you do a twist. In this case, Y inverse X inverse, which just defines an orientation on them, which I'm not going to draw right now. And the traces of these three, of the row images of these three loops exactly determine the representation perfectly. It fully identifies with C3. Every point in C3 has an associated representation into SL2C. Now, if we have some finitely many boundary curves for a surface S, in this case, we only have one boundary curve that we can call K, right there. The curve literally on this boundary component. But in a more general case, if we have n boundary curves for a surface S and some n tuple of complex numbers, then that we call omega, the omega relative character variety from pi1s to g is the subset of the character variety of representations such that the trace of rho of gamma I equals zi for each I, which is to say the trace of the representation of the boundary curves is fixed. The boundary curves have a fixed trace associated to them. This is nice because the mapping class group's action preserves each relative character variety. That's just because the mapping class group is generated by Dane twists, and each Dane twist does not at all affect a boundary curve. A boundary curve is fully off to the side. Even if you twist around a boundary curve, it's still preserved. So it's the trace, so the representation is fully unaffected, as is the trace. And I say that they're preserved by this action. This isn't the same as an open domain of discontinuity necessarily, just because it's not an open set. It's in fact a level set. So if we are allowed to just look at the relative variety and study the action there, though. So in the one-hole torus case, since this is a nice equation we can use for the trace of rho of the boundary curve K, where X, Y, and Z are the traces of X, Y, and Z. If we fix some number K that we want to be set this equal to, then the K relative character variety is just a level set of this function right here for some number K. A lot of good dynamics right there. Oh, clear that. All right. Now here is, actually, let me go on to the next slide first. So if we have some number K and C, then we have nice actions on our relative character varieties that we just defined. So again, our relative character variety is a level set in C3. And so this is one that we can call theta x, where it fixes y and z, but it sends x to yz minus x. There's a similar one called theta y that only affects y, and another for theta z that acts on just z. Now, what do these come from? These are treating this equation right here as a quadratic in each variable. Now, if I go back a ways, right here, this equation here, if we had some fixed k, we just subtract k from both sides, and then we have some equation such that the roots of the equation are the points in the relative character variety. And so over here, the points in this relative character variety are the roots of this equation right here. And let's say you have one root x, y, z, but let's say you're fixing y and z. Well, this theta x just sends x to the other root of the quadratic, the negative b minus x, like here. If we have some equation x squared plus bx plus c, and we have a root equal to x1, then the other root is equal to negative b minus x1. That's a fun fact. And that's what these do. This is the negative b minus x right here in the quadratic equation here. So it at least sends the relative character variety back to itself. And it's also order 2, because then if you do it again, it just sends the negative b minus x1 back to x1. This is nice because we can, this encompasses the action of the mapping class group. If you take two of these involutions, the composition of them is a Dane twist, or at least it's equivalent to the action of the Dane twist on this relative character variety. In particular, it's a bit more than the mapping class group. The mapping class group is an index 2 subgroup of the group generated by these involutions. Again, they're each order 2, and they freely multiply together. There's no relations between them. And so that's a very algebraic action to study in order to talk about the mapping class group's action on these character varieties. So let me clear this and go back a page. This is where I just talk about some miscellaneous tools, examples, etc. So other than the technical space, here's another popular example of an open domain of discontinuity. So we call a representation from the fundamental group of a surface into an isometry group for hyperbolic n space. We call this representation convex co-compact if the action of the image of the fundamental group on Hn, the hyperbolic half plane in R to the n, preserves a convex subspace, and also the restriction of the action to that convex subspace has to be properly discontinuous and co-compact. Here, co-compact means if you quotient the space by the action, you get a compact quotient space. And yes, this is the space of these representations is an open domain of discontinuity within the character variety from pi 1 of s to g. And an equivalent definition we can go over of a representation being convex co-compact is when the orbit map is a quasi-isometric embedding. Now there's some things to define here, but if you're interested, please continue to listen. If we have some generating set for the fundamental group, we define a metric on the group as the distance between two elements being the minimal number of generating elements you need to get from gamma 1 to gamma 2. So like it's like S1 times S2, or like Si times Sj times like some Sk of gamma 1 has to equal gamma 2. And however minimally many S's it takes to get from gamma 1 to gamma 2 is your distance between them. And then the way to define an orbit map from a representation rho and the base point in Hn is you take an element of the fundamental group gamma, and you send it to where rho of gamma sends x naught. Remember here, rho of gamma is an element of the isometry group on Hn. And so a decent picture for this is the fundamental group really looks like this discrete space of points with certain distances assigned between them. And then given hyperbolic half space up here, we have some x naught. And then the identity element gets sent to x naught. And then this element over here that might be like a gamma gets sent to row of gamma, wherever row of gamma sends x naught. And then there's a bunch of other points. And we need this map here to be what's called quasi-isometric, which is to say that the distance between 2 points in the fundamental group here have to roughly stay the same distance between each other in Hn, which has some hyperbolic metric on it. And they have to be the same up to a fixed scaling, where the scaling is like multiplying by some number or adding or subtracting some number, but it has to be the same number for all pairs of starting points. And if the representation creates this orbit map that has this nice distance preserving up to scaling property, then that's equivalent to it being convex co-compact. All right. And now on to the final couple of things. The final thing I'm going to talk about today is the curve complex. This is another application of involutions and is used in many proofs of proper discontinuity on open domains of discontinuity. Given a surface S, we define its curve complex to be a simplicial graph. And this is a graph where simplicial just means it has vertices, edges, triangles, tetrahedra, and simplices as its objects. So there's a vertex for each essential simple closed curve up to isotopy. Essential here means, well, for one non-trivial, it also means not a boundary curve, and it's not homotopic to a puncture if S has a puncture, and also not bounding a Mobius band if S is non-orientable. And so there's a vertex for each isotopy class of these simple closed curves, these loops that don't intersect themselves. And there's an edge between two vertices if the associated curves they represent have representations that intersect minimally. Usually on a surface, this is saying there's an edge between two curves that are disjoint. But I'm trying to draw something. But there are some surfaces where this is useless because any two essential curves always intersect, no matter how you isotope them around. And for example, the one-hole torus is such that thing. So the minimally here means that there's an edge between two curves if they intersect once. So here, these are an example of two curves that intersect minimally on the surface. This loop right here, this loop right here. Similarly, for the four-holed sphere, the minimal intersection number is twice. And there's an edge between two curves that have representations that intersect twice. And we can continue this on. There's a triangle between three curves that pairwise intersect minimally. There's an n simplex between n+1 vertices if pairwise they all intersect minimally. And that's how you build up your graph. Essentially, there is a triangle whenever there's three edges in the shape of a triangle, and etc. for however high the dimension you can climb. And for the one-hole torus, the curve complex associated to it is called the fairy graph. And let me draw that here. And let me first actually draw another representation of the torus. And then I just take a little open disk out of it and identify opposite sides. And each simple closed curve is going to have a slope. Let me start to draw the circle. Consider the circle to be the points that are rational numbers plus the points at infinity. Now I'll start sending some curves over. So the horizontal curve has slope 0, So I'll send it to 0. The vertical curve has well, undefined slope, but vertical slope, we can call that infinity, infinite slope. And notice that these two curves intersect exactly once. Like I said, that's the minimal intersection possible for the surface. So we draw an edge between these 2 points. Now there's actually other edges that intersect both of these exactly once. One of them is the slope 1 curve, right there. Just drawing it away from the um, hole. So that's 1. And that intersects both of these other curves exactly once. So let's draw an edge between those, an edge between those. And notice now that we do have this triangle in the middle that I could fill in, but I'll not, just because this is the highest quality drawing here. Now, it happens that there is no fourth curve that intersects all of these exactly once. So triangles are the maximal size simplex you see in this curve graph. But interestingly, there is another um, curve on here that forms a triangle with this edge. That'll make it the orange, and it's the curve with slope -1. And we'll put that here. And that intersects at least the blue and brown curve once, but intersects the orange curve necessarily twice. We just draw an edge there, the second triangle. And now we can keep going on here. Every curve, every simple closed curve on the one-hole torus is homotopic to this curve with like constant slope on it. So this is a way to talk about every curve. And the way it ends up looking is you draw more edges like that, where they sort of bisect this circumference here, there. And then you do it again for even smaller amounts, and you just keep going down the rabbit hole. Oh, and I totally made too big of a picture, didn't I? Oh, no, that's actually pretty good. All right. And one thing to notice about this picture that again, there are more tools needed to fully justify why it looks exactly this way, but we can look at the dual graph of the surface of this graph by putting a vertex for each triangle and drawing an edge between two triangles that are adjacent to each other and continuing onwards. And what we get here is the 3-valent tree, a tree where each vertex has exactly 3 edges protruding from it, going on into infinity towards the this Q uh, plus infinity. And then also notice that each vertex on the fairy graph becomes a infinite-sided polygon, which is quite interesting. And the way we associate this to everything we've been talking about with character varieties is that the mapping class group acts on this curve complex, as do the involutions. That's just because the curve complex sends one simple closed curve to another simple closed curve, so it sends each vertex to some other vertex. And if two simple closed curves start off intersecting minimally, the curves that get sent to by a homomorphism intersect the exact same amount. So, and if there's an edge between two vertices, there's still an edge between the image of those two vertices via mod of S. And involutions are interesting because they are essentially reflections where let me see. Yeah, let's think about oh, let me just name these things for a second. So the horizontal curve is X, the vertical curve is Y, just as before, and this diagonal curve is Z, and the other is Z prime, which was orange. Now, depending on how we orient x and y, z can in fact be y inverse x inverse, as way back when we talked about the embedding the character variety as C3. And so now what theta z does is here, give me a second. It sends x to x. It sends y to y. And it actually sends z to z prime. It sends it to the other one. That's because z and z prime are the only 2 points that intersect these two, that intersect x and y minimally. And that's the same as saying x, y, z is a triplet on a certain character variety. And it's also, and similarly, x, y, z prime is another triple on a certain character variety. And so it's quite literally a reflection over these lines, because this point right here in the dual graph represents x, y, and z. This point right here is x, y, and z prime. So it flips these two, and the whole curve graph gets flipped with it. And there you have it. These are some tools you can use to study the character variety. I hope this was a helpful talk. And again, if you have any questions, you can email me down here. And yeah.